All right, now we're going to talk about entropy. This is chapter 18, and it says section 4 on here, but I'm not sure if it's section 3, 4, or maybe a combination of both. Either way, we have a little bit to discuss here about entropy. Entropy is basically a measure of disorder. So more entropy means more disorder, less entropy means less disorder. And there is a thing called the law of disorder, or the law of entropy, which basically says that the natural tendency of systems is to move towards disorder or randomness, which means that things that tend to increase in disorder will favor what's called a spontaneous reaction. If you've ever heard of something like spontaneously combusting or just kind of happening on its own, some chemicals can actually kind of happen without much influence, which is considered to be spontaneous. And things that get more orderly don't tend to happen on their own. Like, they tend to take a lot of work in order to make them happen. We're not really going to dwell on spontaneous and non-spontaneous. We're going to look more at the entropy part of things. Here's some examples of entropy. I have the states of matter. As you have the solid over here, everything is very nice and orderly. And then as you go to a liquid, the particles move apart. And as you go to a gas, they move further apart. The amount of disorder is increasing as you go from the solid to the liquid to the gas. And it's pretty easy to tell by looking at the picture. So if you're ever given the option with states of matter, solids would be the least entropy, gases would be the most, and of course if you moved to the left, the entropy would be simply decreasing. Here's an example with chemical reactions. I'm not really concerned so much with the type of reaction, I'm concerned more with the reaction itself, but these were the examples that I could find easily. With this one, I have one molecule. I realize that they're balanced and I have the same number of C's, O's, and CA's on either side. It's not about that. It's about how they're organized. If you just simply look at the molecules, here's one thing together. And on the right-hand side, I have two things, like the Ca and the O are together and the CO2 is together. I went from one piece of stuff to two pieces. That's an increase in entropy then, because it's like one thing broke apart. This is the opposite of that. I have three things that came together to make two. So I have two H2s and an O2. That's three different molecules went together to make two molecules. So the decrease from 3 to 2 is actually decreasing the entropy. It became slightly more organized. So if you're given a chemical equation, you need to look at basically how many molecules or how many pieces of things that you have. More pieces means more entropy, less pieces means less entropy. Another example would be kind of like the arrangement of things. So example, bricks, they're both solids, but how they're arranged, like this is nice and orderly, would be less entropy than this, which is just a pile of bricks. That would be more entropy, definitely more disorder on the right-hand side. The last thing that we're going to do here, which is kind of separate from entropy, is reaction diagrams. This is something that you need to be able to interpret if you look at them. So what I want you to do is I want you to draw these on your note paper. The one on the left I need you to label as exothermic. What this does is shows you the energy of the reactants and the products. And if you can tell by looking at this one, there's less energy on the reactants and more energy on the products. So what this means is you went in, like this much energy from this blue arrow to the top of this one went into the reaction. And then this much energy on the right-hand side came out. So less energy went in than came out. That makes it exothermic. It gave off more than it took in. This little amount right here that you needed to go from the reactants up to the top of this hill is called the activation energy. That's the energy that's needed to start a reaction. On the endothermic one, if you look at it, the amount of energy that went in to get you over this hill was a whole lot compared to how much came out. From the top of the hill down to the products is the energy that came out. So a lot more energy went in. That makes it endothermic. You're looking at the overall change. The activation energy of this reaction is huge compared to the exothermic one. We'll talk a little bit more about these when we get in class.